One of the interesting things about nuclear chemistry, and I say one of the interesting things, but I think everything is interesting about nuclear chemistry and kind of nuclear processes in general, this focus on the nucleus of the atom and what it can do just independent of all the chemical environment around it, is that in a lot of ways, we can model it and think about it in the same way that we do electrons. As chemists, we think about electrons, we think about things like the Bohr model of the atom here, and there's actually a way to model the energy of the nucleons, so the position and the energy of the particles of the nucleus, kind of in their distances from each other and how that relates to their energy. And it's very similar kind of conceptually to the Bohr model. I'm not going to get into what this model is, but I want to talk a little bit about the concepts from it because it helps us to be able to predict what type of nuclear chemistry or what type of nuclear processes are going to occur. So remember, for electrons, we have a way to show the distance. I mean, in the Bohr model, these shells represent energy levels, and as we move away from the nucleus, we increase our potential energy, and so they show both the position and the energy of electrons because of this whole kind of wave-particle duality way that we think about electrons with the Bohr model. And we can do the same thing for the nucleons. And so just like with electrons, we have these shells, right? We have valence electrons, which are these outermost. We can predict how the chemistry occurs based on the movement of electrons and their position on an atom. In the same way, certain configurations of nucleons seem to be favored for particular isotopes. And I want to talk about the different factors that go into that kind of in this little lecture today. So these configurations of protons and neutrons in the nucleus are called and I'm not messing with you, magic numbers. So I love that also. We are scientists, and these are the magic numbers, which are kind of these ratios of protons to neutrons that seem to be favored in a nucleus. And so if we think about protons here, for our protons, these are the magic numbers. 2, 8, 20, 28, 50, 82, and this kind of theoretical 126. And the reason I say it's theoretical is because if we go back to our periodic table of the elements, we know that we've only gotten through the end of period 7 here, which is 118 is our atomic number. So we have 118 protons. Theoretically, if we were to have 126 protons, that would also be stable, although that's not an element that we have discovered yet. So at least with our periodic table, everything after number 82, which is a magic number, 82, everything from 83 on is unstable. And if we look at number 82 on the periodic table, that's our good friend lead. And everything from bismuth on is all unstable all the time. There's actually some exceptions to that. I mean, not the fact that they're all unstable, but there are some things that are all unstable all the time that are below lead, and one of them is technetium. This is number 43. You'll even note that its atomic mass on most periodic tables has fewer significant figures than the others because it is not something that is around very long. Technetium is one of the man-made elements on the periodic table. It doesn't exist on our planet. And then the other one is number 61, which is down here in our lanthanides. PM is promethium. The story of Prometheus, of course, is the Greek legend of the person who gave humans fire, right? Prometheus. So promethium is number 61. It's also unstable, man-made. Most of the lanthanides are fairly stable. They're all below our 83. They have cool properties and they can do other things, but it's not necessarily because of their nuclear properties, as opposed to kind of uranium on, which we talk about as the transuranic elements. Everything after uranium has some interesting and useful properties, especially with things like weapons, right? Uranium, we know, can be used to be weaponized. Plutonium, also in our U.S. history, is quite well known, at least for its nuclear capacity. If you've seen some of my other lecture videos, you know americium is in all of our homes, in our smoke detectors. So the more common ones are the transuranic ones. All right, so for our other ones, 8, 20, 28, 50, for kind of going back to our periodic table, 28 is nickel, 20 is calcium, 8 is oxygen. Doesn't seem like there's a really good pattern, at least in the way that we usually think about the periodic table. The periodic table is the way that we get the patterns, right? It's the one that gives us all the information about the characteristics as they go from one side to another, or kind of whatever the trend line is on the periodic table. But the magic numbers sort of buck that trend, and all of these numbers of protons tend to be the more stable ones. So let's look at number 50 here. When we go to 50 on the periodic table, that gives us tin. So SN, which is from stannum. So tin here, if I was looking at the number of stable isotopes that tin has, there are 10. There's 10 stable isotopes. And we usually think about tin as being in tin cans. So if you think about Campbell's soup in a tin can, then it's made up of some combination of those 10 stable isotopes, because all 10 of them exist here on our planet. So there's lots of ways that tin likes to be tin. So there's something about 50 that's a magic number. But if you look at either side of tin, so here's number 50. If we go to 49, that's indium. And if we go to 51, that's stibium or antimony. So antimony is one of our metalloids. Indium is on the other side and is one of our transition metals. So you would think that indium would have slightly more in common with tin than antimony would. But regardless, antimony and indium, at least in the context of our isotopes here, have more in common with each other because they each only have 2. So again, same position on the periodic table, relatively speaking, but quite a difference in the stability of the the stability of the isotopes that form based on the number of nucleons. So there's something special about this number of protons. They're magic, if you will. And nature seems to appreciate even numbers in general. If you look at all of our magic numbers here, they're all even for a number of protons. And if we look at the mass number, which includes the mass of the atom, which is the total number of neutrons and protons, so the total number of nucleons, the number of stable isotopes with even numbers of nucleons, of protons and neutrons, is 157. So I think it's a little bit, ironic that it's an odd number, but whatever. So there's this many isotopes that are stable, that have an even number of nucleons. The total number that are stable with an odd number of nucleons is 5, right? So there's this heavily weighting towards even numbers, not necessarily even in terms of the same number of protons and neutrons, although we're kind of get into that in a second. But really, in terms of just having those even numbers, there's something special about it, and kind of leave that to the particle physicists to get into the details of it. But for right now, this is just kind of an interesting trend, at least from a nuclear chemistry standpoint. Okay, so if we're thinking about stability then, if we know something about the nucleus and we know something about our elements, then we should be able to predict the type of radioactive decay that it is undergoing in order to get to a more stable format. Because we know for radioactivity that the name of the game is to get to a more stable configuration. So there seem to be these magic numbers. There seems to be some magic ratio of even numbered nucleons that seems to lead to better stability. So all radioactive processes are trying to get towards those ratios. They're trying to get towards those magic numbers. And anything out of this ratio, this band of stability, is going to be unstable. And we can tell by looking at this neutron to proton ratio. And there's actually a graph that I'll show you in just a second that looks at the number of neutrons compared to the atomic number. And that gives you this band or region of stability. I like band of stability because it makes it sound like some sort of like hardcore punk band. It's the band of stability. So if we're looking at this ratio then, the larger the ratio, the larger the N to Z ratio, that is usually going to give us beta emission. And the reason that it would give us beta emission is because it's going to increase our Z, and that will decrease our number of neutrons. So remember, Z, for reasons that I will never understand, is the symbol for atomic number. So it increases the number of protons, decreases the number of neutrons. And so if I have a larger N to Z value, if I'm thinking about this band of stability, then this is going to be kind of to the left of my band. Left of band of stability. All right, so let me show you what this looks like, and then we'll come back to my notes here. So this band of stability, here, this straight line up the middle of my graph here is a 1-to-1 ratio of neutrons to protons. So if I had a 1-to-1 ratio, here's 10 to 10, 20 to 20, 30 to 30, then that's this line for reference, right? And for the most part, at least for that early part of the periodic table, the most stable configurations follow that 1-to-1 ratio pretty well, right up through about, 10, 12, kind of in that kind of range. And then they start to push off to the side here, and it's pushing off to the side because we're getting a greater number of neutrons needed as we get a greater number of protons. And the reason for that is sort of the weird inexplicability of the nucleus, right? There's these two conflicting forces, the force that's holding it together, that strong nuclear force that works under very short distances, and electric repulsive force, which is these like charges that we're putting in very close proximity, these positively charged protons that want to push each other apart. So we need more glue, we need more neutrons in there to help to make that more stable. And so these neutrons, we have an increasing number, and this is our band of stability, or valley of stability is the way that it says here, or region of stability. Okay, so if we have more neutrons than we do protons, then we need to get more protons and fewer neutrons. And so in order to do that, that would be something like beta decay. If I have a smaller N to Z ratio, and again, this is the mass number minus the atomic number here on the y-axis, which is still number of neutrons. If I have a smaller ratio, meaning that I have something to the right of the band here, then I need to have an increasing number of neutrons and a decreasing number of protons. And so that would give me something like positron emission or electron capture. So this is kind of my band of stability, this region of stability right here. And actually there's what is called the island of stability out here somewhere. And you can kind of get into all the details of all the isotopes if you look at all the different options here in more detail on a larger scale. You can see all sorts of interesting images. Another one, just to mention it, is the alpha decay. So alpha particles, of course, are 2 protons and 2 neutrons. And so if you're trying to get to a more stable configuration, but you sit along this line somewhere, right? So this is kind of to the left of the band. This is to the right of the band. If you're kind of further up the band, but more to 1-to-1, you just need to get back down into a more stable area. And so one way to do that is by losing both protons and neutrons, which would push you back down into these lower levels. And that's what alpha decay is going to give you. Or fission, which is just going to split you apart into smaller pieces. You just need to get smaller because you've gone too far off into the sunset here. Okay, so if we're kind of capturing that, then that larger N to Z, that left of the band, is usually this beta emission because it increases the number of protons and decreases the neutrons. The smaller neutron to proton ratio is to the right of the band. And that's going to be the nuclear decay that's going to happen in order to kind of get you back into that band of stability is either positron emission or electron capture, which is going to, it's going to decrease the number of protons and increase the number of neutrons, which will push you back into the band, right? And that's kind of the important bit there, is moving back into that region of stability. Because again, the name of the game is this region of stability. This is where all the stable isotopes are hanging out. And so there's different ways that we can undergo radioactive or nuclear change in order to get there. And those stable isotopes are going to be the ones that have the even numbers, and they're going to be the ones that have these magic numbers of protons. And kind of putting that all together gives us a way to then predict about the radioactive decay for these radioactive elements. Pretty cool, huh?